The mechanic was 23 years old, from Huntsville, Alabama, and the inside of his nose was freezing shut. It was February of 1950, a little after 4 in the morning at Eielson Air Force Base, 26 miles southeast of Fairbanks. The thermometer on the side of the hangar read 40 below, and at 40 below, Fahrenheit and Celsius agree on the number. They agree on nothing else. The air burned. Metal tools, if you picked them up barehanded, took a layer of skin with them when you let go. Above him loomed the tail of a Convair B-36B Peacemaker, serial 4492075, 162 feet of magnesium and aluminum stretched against a sky so dark it looked like the inside of a coal stove. The bomber's 6 Pratt & Whitney R4360W Wasp Major engines sat cold in their nacelles, each one a 28-cylinder corncob displacing 4,360 cubic inches. Each cylinder had 2 spark plugs, 56 per engine, 336 per airplane. Every one of them had to fire. Every one of them had to fire in this cold. The mechanic had been told, in the polite language the Air Force sometimes mistakes for clarity, that if you shut these engines down at these temperatures, you could not restart them. Not that it was difficult, you could not restart them. The oil became the consistency of cold honey. The batteries lost 2/3 of their cranking amperage, and when the starter finally turned the prop, a single misfire on a single cylinder would coat a plug with unburned fuel that froze into a glaze of ice across the electrode gap. The engine, stone dead, would refuse to fire until someone pulled the cowl, unscrewed the plug, warmed it in his hands, and screwed it back in. Now do that 56 times on an engine buried in a wing, at 40 below, in the dark. This is a story about a small thing, a ceramic cone the size of a shotgun shell, and the men and women in Flint and Toledo who learned how to make it survive a kind of cold the United States had never had to fight in before. Without that ceramic, there is no Strategic Air Command, there is no deterrent. There is no bomber circling the pole at 40,000 feet waiting for a coded order that, thank God, never came. The spark plug is the whole Cold War in miniature. Get it wrong, and the engines do not start, and the bombers do not fly, and Moscow learns something about American resolve the Politburo would have been pleased to learn. The problem was physics, and physics does not care about politics. A spark plug is asked to do something preposterous. It must fire between 90,000 and 150,000 times an hour. It must survive temperatures of 1,200 degrees Fahrenheit on its firing tip, while the other end, 2 inches away, may be only 180. It must jump an electric arc of between 6,000 and 20,000 volts across a gap roughly the thickness of a nickel inside a combustion chamber filled with burning high-octane fuel at pressures that would burst a cast iron pipe. It must do this for hundreds of hours, across years of service, and it must never, not once, not even for a single revolution, fail to do it on command. The tip of the plug has to run hot enough, at least 800 degrees Fahrenheit, to burn off carbon and the lead deposits left behind by tetraethyl lead in aviation gasoline. If it runs any colder, the carbon accumulates, the gap fouls, the spark fails. The cylinder misfires, and when one cylinder of a 28-cylinder engine misfires, the whole engine shudders and pulls against itself, and a flight engineer 40,000 feet over the Arctic Ocean watches a dial swing the wrong way and begins to calculate how much time he has. So the tip must be hot, but the upper end of the plug, the terminal where the ignition harness bolts on, must stay cool because the electrical insulation cannot tolerate combustion chamber temperatures without breaking down. The whole business rests on a single part, the ceramic cone in the middle. That piece of fired white material, no bigger than a candle stub, has to conduct heat well enough to dump combustion temperatures down into the cylinder head, but insulate well enough to force tens of thousands of volts through a tiny gap rather than leaking sideways into the metal shell. Heat conductor, electrical insulator. The properties are almost opposites. Find a material that balances them and the engine runs. Fail to find one, and you have a very heavy sculpture. For 50 years, spark plug makers had been trying to find it, and for most of that time, they got it wrong. The first spark plugs used refractory porcelain, a kiln-fired material based on kaolinite clay, the same stuff potters use for fine white dishes. It held up in early automobiles, where engines ran at modest compression and pilots did not exist. But the porcelain was brittle, and as engines grew more powerful, the little insulators cracked. Then came mica, thin translucent sheets of the mineral compressed into a cylinder by tension on the center electrode. Mica tolerated heat better than porcelain. It was the material of choice for aviation plugs through the First World War and into the Second. But mica had a fatal weakness. It was a laminate. Lead salts from the combustion crept between its layers. The cleaning intervals shrank from hundreds of hours to tens, and in a four-engine bomber, that was a maintenance burden the peacetime Army Air Corps could absorb only because it did not fly very many of them very far. Then came sillimanite and andalusite, two related aluminum silicate minerals, sister crystals of the same chemistry found in ancient metamorphic rock. Champion Sparkplug in Toledo, AA, had locked down the American supply, mining most of it from a single site called the Champion Mine in Inyo County, California. Their dominance of that one mountain gave them dominance of the plug market through the 1930s. A plug with a sillimanite insulator was tougher than porcelain and cleaner than mica. But sillimanite was a compromise, and everyone knew it. Something better was coming. That something was sintered aluminum oxide, alumina, Al2O3, a simple compound, 2 aluminum atoms and 3 of oxygen, held together by one of the strongest ionic bonds in nature. Heat it to 1600 degrees Celsius, compress it, and you get a ceramic with nearly the thermal expansion of steel, 3 times the strength of sillimanite, and dielectric properties that let it hold back 60,000 volts across a thickness smaller than a pencil eraser. Siemens in Germany and AC Sparkplug of Flint, Michigan had both developed versions of sintered alumina during the 1930s, but the process was expensive, the advantages were incremental, and the war came before anyone was willing to retool the factories. The Cold War did not give that luxury. The Cold War demanded alumina. By the time the bombs fell on Hiroshima, both American manufacturers, AC Sparkplug, a division of General Motors, and Champion, the Toledo independent, were beginning the conversion. By 1948, alumina had essentially replaced every mineral-based insulator in American aviation plugs. The sillimanite mine quieted down. In Flint and Toledo, the kilns ran 20 hours a day. They had to, because the airplanes about to be built would not be built for temperate war. Anyone who has seen a photograph of Thule Air Base in midwinter knows the mood. The base sits at 76 degrees north latitude, about 900 miles from the geographic North Pole, on a gravel plain where the sun does not rise for 4 months. Construction began in 1951 under the codename Operation Blue Jay. Most of the buildings went up in the first 60 days by men working in temperatures that shattered hydraulic hoses and made diesel fuel gel in its tanks. The finished base had a 10,000-foot runway, 10 hangars, and fuel storage of roughly 100 million gallons. At its peak, 10,000 Americans lived there. They were there because, if the war came, Thule was where the bombers would launch from. The Great Circle route from Greenland to Moscow is shorter than the route from Kansas. The Air Force built Eielson in Alaska for the same reason. Both bases served as what planners called forward operating locations, polite bureaucratic language meaning the place from which you would fly the mission that would end everything. And so the United States Strategic Air Command in the early 1950s found itself holding the keys to a strategic doctrine that depended on an engineering problem nobody had fully solved: how to start a very large reciprocating aircraft engine reliably in temperatures that could reach -60 Fahrenheit on the ramp. The demand was ferocious. The B-36 Peacemaker had 6 R-4360s. Each R-4360 had 56 spark plugs. A wing of 30 bombers needed more than 10,000 plugs just to fly. Replacement was constant. A B-36 flight engineer wrote that changing all 56 plugs on a single engine was a full day's work for a qualified mechanic. Multiply that across an entire theater. Multiply it across the KC-97 tanker fleet, each with 4 R-4360s of its own. Multiply it across B-50s and C-124s and P-2V Neptunes patrolling for submarines in the North Atlantic. In the winter of 1956 and 1957, according to the base records at Thule, 3 KC-97 tankers were readied for a reconnaissance mission at temperatures of -46°C. 5 tankers were pre-positioned. The operational goal was brutally practical. Get 3 airborne from a starting pool of 5, because the margin for failure was that narrow, and because the spark plugs and the oil and the magnetos and the carburetors and the batteries and every other component in the starting chain had known failure rates, and at those temperatures, no one of them could be trusted on its own. This is what the men of Cold War Archives audience remember, if they were there. The preheaters roaring, fuel-fired heaters the size of compact cars wheeled up to the nacelles under canvas skirts, the ground crews in white bunny suits walking inside mazes of hot air ducting, the constant shrieking whine of auxiliary power units, the smell of avgas and propane and hydraulic oil freezing on concrete, and the engines. The big corncob radios coughing, blowing smoke rings the size of hula hoops, firing on one bank of cylinders, then another, then, if the plugs held, all of them. A 1,400 horsepower sigh of machinery finally deciding to live. If a plug failed, the cylinder did not fire. If the cylinder did not fire, fuel pooled. If fuel pooled, it drained into the lower cylinders of the radial, and on a radial engine, fuel in the lower cylinders can hydraulically lock a piston. Hydraulic lock on start means a bent connecting rod. A bent rod means an engine removal. An engine removal in Thule in February means a crane crew outside for 6 hours in -50. And somewhere, in an office in Washington, someone marks an asset as unavailable. You can see now why the ceramic mattered. The breakthrough that made Cold War strategic air power possible did not happen in a single laboratory on a single day. It was incremental, the product of thousands of small adjustments by chemists and ceramic engineers at AC Sparkplug in Flint and at Champion in Toledo, and later at Bendix Scintilla in Sydney, New York, which produced the low-tension magnetos and fine-wire plugs specified for the B-36's ignition system. The technical problem was this. The ceramic had to be made of nearly pure alumina oxide, but nearly pure alumina is almost impossible to sinter, to fuse into a dense solid, without tiny additives called sintering aids. These additives lower the melting point of the grain boundaries and allow the particles to bond together without the whole piece collapsing. The trick was to add enough to sinter, but not so much that dielectric strength suffered. Early formulations ran around 95% alumina and 5% glass former. Over time, manufacturers pushed that ratio higher toward 98 then 99% pure alumina, using small amounts of magnesium oxide, silicon dioxide, and rare earth additives like yttrium and lanthanum to control grain growth. The center electrode was a separate problem. A solid nickel wire worked at moderate temperatures, but the fine wire aviation plug specified for the R4360 used a center electrode of platinum or platinum-iridium alloy surrounded by a copper core that pulled heat down into the body of the plug. In the early 1950s, a single fine wire aviation plug cost more than a good wristwatch. A B-36 flew with 336 of them. The proof came in the test cells at East Hartford, Connecticut, where Pratt & Whitney ran engines against a wall of instrumentation in enclosures built to absorb the noise and, if it came to it, contain the fire. Engines were started cold. Engines were started hot. Engines were started after being soaked at simulated altitude, -65 Fahrenheit at 40,000 feet. The spark plugs held. Flashover across the ceramic, the electrical leakage that had plagued porcelain dropped to almost nothing. The carbon burn-off was clean. The ice over its startup remained, and preheat remained mandatory, but the plugs themselves, once lit, stayed lit. That was the breakthrough. Not that the plug solved the cold problem by itself, but that the plug stopped being the weakest link. The plug was no longer the reason the engine failed to start. Everything else, the oil, the battery, the carburetor, the magneto, could be addressed with heaters, with multi-viscosity lubricants, with external power carts. The plug, for the first time since men had been putting wings on radial engines, could be assumed. There is a building on the south side of Flint, Michigan, or there was before the wrecking ball got it, that deserves a sentence in every history of the Cold War and almost never gets one. The AC spark plug division plant on Dort Highway employed somewhere between 15 and 20,000 people at its peak in the early 1950s. It made the bulk of the aviation plugs used by the United States Air Force. During the Second World War, the same plant had built one of the largest numbers of Browning M2 50-caliber machine guns of any American facility, but that is another story. After the war, the machine gun lines were torn out and the plug lines expanded. The building smelled of electroplating acid and ceramic slurry and the vinegary tang of hot glaze. The floor vibrated at a specific frequency, a low hum caused by 1,000 single-station presses compacting alumina powder into the rough shape of an insulator, each press cycling about 4 times a second. Most of the operators were women. Some had started during the war making machine guns and stayed on when the lines changed. Others had been hired out of the small farming towns north of Flint, Clio, Mount Morris, Birch Run, when their husbands came home from the Pacific and the family needed a second income. They stood all day at benches sorting finished insulators for cracks under a row of magnifying lamps. A chipped ceramic, undetected, would cost an engine in a bomber. They knew this. Nobody had to tell them. Champion, in Toledo, ran a parallel operation. So did Autolite. And on a smaller scale, so did the ceramic division of a company called Coors. Yes, the same Coors. The brewing family had started in porcelain long before they were famous for beer, and the Coors Porcelain Company of Golden, Colorado made ceramic components for a range of American industrial needs during the Cold War. Small items, critical items. At AC, a finished aviation plug passed through an inspection station where a technician, almost always a woman, almost always with decades of experience, placed it in a pressure fixture and tested the ceramic at high voltage under simulated combustion pressure. Plugs that leaked were rejected. Plugs that cracked were rejected. Plugs with a visible flaw in the glaze were rejected. 1 plug in 5 ended up in a scrap barrel. Those scrap barrels fed back into the raw material chain. Alumina is, in that sense, a forgiving material. It can be ground back down and refired. The Flint plant ran 3 shifts through the coldest years of the Cold War. It fed a pipeline that stretched from Dort Highway to Wright Field in Ohio, to Pratt & Whitney in Connecticut, to the flight lines at Eielson, Loring, Thule, Goose Bay, and in time, Lajes and Torrejon and Guam. When a B-36 in Alaska needed 3 dozen replacement plugs, the plugs had been made in Flint by a woman whose brother probably had flown in another airplane over another ocean 8 years earlier. The supply chain was human. It always is. The bomber got in the air. Sometimes it did not come back. On the night of February 13, 1950, the B-36B that opened this story, serial 44-92075, lifted off from Eielson carrying a Mark IV nuclear bomb as part of a training mission to simulate a strike on San Francisco. The ground temperature, according to the weather logs and subsequent investigation, was -40 Fahrenheit. The engines had been preheated. The spark plugs, presumably, had been inspected. The checks had been run. The bomber climbed out over the Gulf of Alaska and turned southeast. 7 hours into the mission, the crew reported flames shooting from 3 of the 6 engines. The other 3 could not maintain altitude on the nuclear payload. Investigators later concluded that ice had formed in the carburetor air intakes. The cold hadn't finished with the airplane just because the engines had started. It was still there, waiting at altitude. The captain, Harold Barry, ordered the Mark IV jettisoned over the inside passage of British Columbia, where its conventional explosives detonated as designed, preventing any recovery of the weapon's components. Then he ordered the crew to bail out. 12 of the 17 men aboard survived. 5 did not. The B-36 itself, on autopilot, flew on for another 200 miles before crashing into Mount Kologat in northwestern British Columbia, where its wreckage was not discovered for more than 3 years. It was the first broken arrow in American history, the first loss of a nuclear weapon. Nobody blamed the spark plugs. That is the point. By 1950, the plugs were reliable enough that when things went wrong, the investigators looked elsewhere, to induction icing, to fuel system anomalies, to the pilot's decisions. A decade earlier, a mission like that, at a temperature like that, would have been blamed on ignition almost as a reflex. By the early Cold War, ignition had become the part of the airplane that worked. There are quieter stories. A B-47 crew chief at Eielson in 1958, this from a unit history written many years later, recounted pulling a single fouled plug from a Stratojet's J-47 engine after an alert launch exercise. The plug coming out coated in a film of ice the thickness of cellophane. They replaced it in under 4 minutes. The airplane made its next takeoff window. There was no drama. There was no combat. But somewhere in Moscow, a photo reconnaissance officer noted that American bombers continued to go and come from Alaska on their expected schedule even in the worst weather of the year, and drew from that the conclusion that Strategic Air Command meant what it said. Deterrence is built out of things that work without being noticed. What the Soviets did differently is itself a study in the asymmetries of empire. The Soviet Union had a lot of extreme cold, more of it, more reliably, than any part of North America outside Alaska. Soviet engineers had been wrestling with sub-zero engine operations since the 1930s, and by the Cold War, their doctrine had crystallized around a different approach. Do not build precision components and then protect them. Build rugged components and let them take the beating. The V2 diesel tank engine, later the V46 that powered the T-72, is the icon of that philosophy. Loud, smoky, unrefined, capable of running while leaking oil, burning unfiltered fuel, or, as one Western analyst put it, missing a cylinder or two. For gasoline engines, including the aviation power plants in early jet fighters and propeller-driven bombers like the T-4, a reverse-engineered B-29, spark plugs and all, the Soviets relied on a combination of heavy preheating, fuel-fired under-wing heaters, and, in some documented cases, open-flame warming of the engine compartment using a controlled burn of aviation fuel beneath a nacelle. This last technique, remarkably, had been learned from the Soviets themselves by Luftwaffe mechanics in the winter of 1941 to 1942 on the Eastern Front, when German pilots could not keep the oil fluid in their Messerschmitt Bf-109s, and a captured Soviet airman showed them how to thaw an engine by igniting fuel beneath it. The German approach in the Second World War had been chemical ingenuity applied too late. They had fuel injection before the Americans. They had direct injection cylinder heads. But their spark plugs made by Bosch and Beru used ceramic formulations that were excellent for temperate European operations and brittle at the true extremes of the Russian winter. The Wehrmacht lost more tanks and aircraft to cold starting failures in the first 3 months of the Eastern Campaign, by some accounts, than to Soviet combat action. The spark plug is not the whole explanation, but it is part of it. The Japanese were further behind still. Japanese industrial ceramics in the 1940s were first-rate for porcelain and for artillery fuses, but aviation-grade sintered alumina was a technology Japan did not develop in volume until the post-war occupation era, when NGK, a company whose name most American drivers know, began its rise by licensing and then improving on German and American insulator technology. By the time NGK was a serious global competitor in the 1960s, the Cold War Arctic aviation problem had already been solved by the Americans. The asymmetry matters. Both Moscow and Washington wanted the capability to project bombers over the polar cap. Both faced the same physics. The American answer was a million-part industrial system in which the ceramic cone in the middle of a spark plug was one of the most refined industrial products in the world. The Soviet answer was an engine so rugged that it did not care whether a plug or two misfired for the first few minutes. Both worked in their own way, but only one of them worked while also producing a B-52 with 8 jets and a 10,000-mile combat radius. The companies aged into the long post-war. The AC spark plug division was folded in 1974 into what General Motors by then called AC Delco, a merger with Delco Remy, the old Dayton Engineering Laboratories company where Charles Kettering had invented the electric self-starter 60 years earlier. The Flint plant survived until 1988, when plug production moved elsewhere within GM and the building was demolished. Today, most of the spark plugs sold under the AC Delco label are manufactured by NGK in West Virginia under contract, a fact that would have astonished the women in Flint who sorted ceramics in 1953. Champion spark plug became part of Federal Mogul, which was eventually absorbed into the auto parts conglomerate Tenneco. The name survives. The plug on your lawnmower may still say Champion on the side. The company that Albert Champion founded with his brothers in Boston in 1905 is a brand now, not a place. But the technology endures with remarkable constancy. If you pull a plug from a 2026 pickup truck and set it beside one pulled from a 1954 B-36, the differences are in the details of metallurgy and thread form. The ceramic is the same material. The basic design is the same design. An aviation mechanic from the Cold War could service a modern aviation engine without retraining on the ignition system. That is unusual. Most Cold War technologies have been superseded. Vacuum tubes replaced by transistors, replaced by integrated circuits, film cameras by digital sensors, slide rules by handheld calculators. The spark plug is one of the very few pieces of American mid-20th century industrial engineering that is still essentially what we use today. What the men and women of Flint and Toledo developed for the B-36 is, in miniature, under the hood of every gasoline-powered vehicle you will pass on the highway tomorrow morning. Come back to the mechanic. Eielson, 1950. 4 in the morning, 40 below. He does not know any of this yet. He does not know that the alumina cone in his toolbox is the product of a half-century of ceramics research that was completed almost by accident, just in time to support the air strategy of the nuclear age. He does not know that the women in Flint who made his replacement plugs will, many of them, still be alive when the Soviet Union falls and will watch the news that night and wonder quietly whether anyone remembers what they did. He does not know that the B-36 he is about to send into the sky will itself be lost, that ice will foul its carburetors, that the bomb it carries will be jettisoned over British Columbia and not found for 70 years. He knows only that his fingers are numb and that the plug in his hand must thread into its port without cross-threading, and that the torque wrench must click at 40 foot-pounds, and that the ignition harness must screw back on with its 3/4 20 connector and seat true, and that the whole assembly must be repeated 55 more times on this engine alone, and then 335 more times on the rest of this airplane, and that he has 2 hours to do it before the crew arrives and the engines are preheated for the scheduled departure window. There is a photograph. It hangs, or once hung, in the small base museum at Eielson of a ground crew lined up beside the nose of a B-36 in deep winter, circa 1952. 9 men, all parka-hooded, all with frost in their eyebrows, none smiling, because nobody smiles at 40 below. The caption identifies them only as Maintenance Personnel, 97th Bombardment Wing. They are standing in front of an airplane that is going to fly. They are standing in front of the reason it is going to fly. It is a strange thing to stake a civilization on a ceramic cone. Strange to stake deterrence on grain boundaries a few microns across, on the dielectric strength of a material whose recipe was perfected by a chemist most Americans have never heard of, working in a division of a corporation that no longer exists. Strange that the whole architecture of mutually assured destruction, the B-36 over the pole, the KC-97 tanker waiting at Thule, the Alert 5 Stratojet with its engines turning on the ramp at Eielson, rested on a part that the men who installed it could hold in one gloved hand. But it was not strange to them. They were professionals. They installed the part. They torqued the wrench. They cleaned the ceramic with solvent and inspected it under a flashlight for the hairline crack that would kill an engine at altitude, and then they moved on to the next cylinder. The sun did not come up for another 4 hours. The bomber took off anyway. The spark plug fired. It always fired. That was the point. And somewhere in Moscow, a general looked at a photograph of an American airfield in winter, engines turning, crews loading, the ordinary morning of a force that was never, on any given day, entirely on the ground, and made a decision. Not the decision to surrender, not the decision to escalate, the decision rather to wait, to hold, to let another day pass without the war. That decision was made, in part, because a small white ceramic in a gloved hand at 40 below would not, under any circumstances, fail to do its job. It is a strange monument, but it is a monument.